The second derivative test is a test we can do to check and see if a critical point on a function is perhaps a local max, perhaps a local min, uh, or perhaps neither. But to verify that, we would have to use the first derivative test. So the second derivative test is an alternative to the first derivative test to help see if critical points are local maxes or mins. Sometimes the second derivative test fails, and we'd have to verify using the first derivative test, but it is still useful because it is a lot quicker to do than the first derivative test. And if you don't know what I'm talking about in terms of first derivative test, go back and watch that video to make sure you understand before watching this one. So here we go. Okay, this example says for the function below, find the critical points, then classify them using the second derivative test. So I should remind you what critical numbers are before we do this question. So critical numbers are numbers that make the derivative equal 0 or undefined, and are also in the domain of the original function. And if we know that it makes the derivative equal to 0, well then we know we have a horizontal tangent there. So therefore it could be a max or a min point, or it could be neither, right? It could be a max, could be a min, could be neither. We're going to use the second derivative test to hopefully tell which of those scenarios it is. So let's start by finding the critical numbers. So that would be any number that makes the derivative, and I'll find the derivative quickly here. Anything that makes this derivative be 0 or undefined. Well, this is a quadratic, so there's no way it could be undefined, but it could be 0. Let me set it to 0 and solve. I'll common factor out of 3x. I get x minus 2. So I have it in factored form now. So this product could be 0 if 3x was 0, or if x minus 2 was 0. So if x was 0 or 2. So I have two critical numbers. So these numbers here, these are called critical numbers because those are numbers that make the derivative be 0, which means at those x values on the original function, there is a horizontal tangent, meaning it could be a max or a min point. Let's figure out if it is a max or a min point. Well, I guess before I do that, maybe we should get the y values that go with these x values on the original function. So let's figure out what is g at 0. If I plug that into the original, I get 2. So 0, 2. If I plug 2 into the original function, I'll get 8 minus 12, which is negative 4, plus 2, it's negative 2. So 2, negative 2. So these right here are our critical points. Critical points. So there are points on the original function that have a horizontal tangent, right? They have a tangent slope of 0. That's what we set the derivative equal to and solved for. So they have tangent slopes of 0, which means they could be max or min points or neither. So what we're going to do is do the second derivative test to check. So I've set up a table here for this. I mean, we don't have to do a table, but it's a nice way of organizing it. So I've got my two critical numbers. I've got 0 and 2. And what I'm going to do is I'm going to check in the second derivative what is the sign of the second derivative at those x values. So how is that going to help me? Well, I've told you at these 2 points, 0, 2, and 2, negative 2, it could be a max, could be a min, or it could be neither. How is the second derivative going to help us tell if it's a max or a min? Well, if you notice the function at that x value right there, at that critical point, it's concave down. And the second derivative tells us the concavity of the original function, right? The second derivative is negative, right? If g double prime of x is less than 0, we'd have this scenario. If g double prime of x was greater than 0, we'd have this scenario. It would be concave up, and it would be a min point. So it would be max in this scenario, it would be min in this scenario. So let's see what we have. Well, we're going to need the equation of the second derivative, right? Second derivative tells us the concavity of the original function. So let's find the second derivative. So g double prime of x. So here's my first derivative, 3x squared minus 6x. So my second derivative would be 6x minus 6. So let's see what the concavity of the original function is at these two critical numbers, at 0 and 2. Well, at 0, if I plug that into the second derivative, right, g double prime of 0, I would get negative 6. So it would be negative. That tells us the original function is concave down at the x value of 0. So meaning it looks like this, which means it must be a max point. So we have a max. I should write local max. It's a local max at 0, 2. How about at the x value of 2? If I plug 2 into the equation of my second derivative, g double prime of 2 would be 12 minus 6, which is positive, which tells me the original function is concave up, which means it looks like this, which means the point 2, negative 2 is a min. So 2, negative 2, local min. Okay, so that's how you use the second derivative test to classify a critical point as either a local max or a min. You just check the second derivative to see if the original function is concave up or down at that point, and then that should indicate to you whether we have this, a local max, or this, a local min. Now, I should mention to you that the second derivative test sometimes fails. Like, for example, let's think about the function y equals x to the 4. Just quickly, we know roughly what that looks like. It looks something like this, y equals x to the 4. It does have a local min point at 0. But the second derivative test would not reveal that to us, and let me show you. So the first derivative is 4x cubed. Any critical numbers, so any zeros of this, would be potential max or min points. So how could this be 0? Well, this would be 0 if x was 0. So x equals 0 is a critical number, so it's a potential max or min point. I mean, we know from the graph it is a min, but let me show you how the second derivative test actually fails us here. So second derivative test, we'd look at the second derivative, we'd get 12x squared, and then we would want to actually test the x value, the critical number, into the second derivative to see if this function is concave up or concave down at that point. So we'd plug 0 in, y double prime at 0, and we would get 0. So that indicates to us that it's not concave up or concave down at that point. So the second derivative test actually failed there. It didn't tell us it was concave up, indicating a local min. So when that happens, when you try the second derivative test, right, if your second derivative of some function is 0, that indicates to you that the test fails. So the second derivative test fails. So what do you do in that scenario? You have to go and do the first derivative test, where you test for intervals of increasing and decreasing around the critical number. So you would have to test a point less than 0 and a point greater than 0 into your first derivative, and see that the you could test -1 into here, and you'll get -4, which indicates that the function is decreasing before this point. And then test 1 into here, you'll get +4, indicates it's increasing after, and that would tell you that it's a local min. So if you try the second derivative test and you get 0, that indicates it fails. It doesn't mean you don't have a local max or a min, it just means you have to try the first derivative test to verify. So I hope you understand what the second derivative test is. Let me just show you the Desmos version of what we were working with in the first example. So here's that x cubed minus 3x squared plus 2 function that we did our example with at the beginning. So notice I've highlighted the concave down portion of this function in green and the concave up portion of this function in orange. So we found two critical numbers. We found there was a horizontal tangent at x equals 0. So let me just set the x value to 0. See, horizontal tangent there, and also just to verify, notice the value of the first derivative, 0, there, and also at 2. Horizontal tangent in those two places. So how did we use the second derivative to verify whether we had a local max or a local min point? Well, at an x value of 0, let me put that back to 0, notice the value of the second derivative was negative. That indicates that the function is concave down at that point, which means it's a max. And then also at the x value of 2, we found out the second derivative was positive, which indicates it's concave up at that point, indicating that it's a local min point. So hopefully that video made sense for you. Make sure you like and subscribe. If you haven't subscribed to the channel yet, make sure you do that so that you can stay up to date with all the videos that I'm posting for the Calculus and Vectors course. Also, if you want a list of the rules for how to do first and second derivative tests, here they are. Feel free to pause the video and read those rules. But make sure you understand both of these tests, first and second derivative test, are ways of classifying critical points as either local max or min points. So go back and watch the video on first derivative test if you forget that one. And this video is all about second derivative test.